Hello and welcome to today's video. Today's video is for Advanced Geometry, Chapter 1, Section 6, Measuring Angles. So we start out with the definition of an angle. An angle is formed by two rays with the same endpoint. The rays are called the sides of the angle. So there's a couple different ways we can name angles. So I'm actually going to draw a couple angles. So I'm going to draw three rays and have them share a vertex. So put some points on it. We'll call this A, B, C, D. Now, if you take a look at what I have, I cannot call any of these angle B. The reason why is because I've actually got multiple angles. I've got this angle right here, I've got this angle right here, and I also have the big outside angle ABC, which also could be called angle B. So anytime there's any ambiguity in what angle is being referred to, you cannot name an angle with a single point. Okay? So, for example, if I had a single angle all by itself, I can call this angle E. But in this picture, the one on the right, I would have to use 3 points to name the angle. I could call it ABD, I could call it DBA. So I'll put a couple examples. So this would be angle ABD or angle DBA. The only thing is the middle point needs to be the vertex. I can also name these angles with numbers. So if I put a number 1 here and a number 2 there, I can call them angle 1 and angle 2. So, or angle 1. So that top angle can be called ABD, DBA, or angle 1. So the one at the bottom, they say name angle 1 in 2 other ways. So when I look at it, angle 1 I can't call angle E because E is the vertex of angle 2 also, and it's also the vertex of the angle that would be a combination of 1 and 2. So, but what I can do is I can use 3 points. So I can call it angle AEC or angle CEA. The next thing I have is just to get you familiar with what we're going to be doing next, the protractor postulate. It seems, if I just show it to you, it seems like it's really wordy, really long, and really complicated, and it really is such an easy concept. So I start out with a little protractor, and I say, what's my measure? So we're good at this. I have one side of the angle lined up with 0, so the other side of the angle is the measure of the angle. So this is 70 degrees. Done. The next one, though, I alter a little bit. Now I did not put one side of the angle on 0 degrees. You can still figure out what the angle is and not move the angle so it's lined up with 0. What you can do is you can find the length or the measure of the angle from 0 all the way over to one side, and this is 130 degrees. And you can also find the measure from 0 all the way to the second side, and that's 70 degrees. And then what you can do is to find the measure of the angle in between them, you just subtract them. So this angle is going to be 130 minus 70, which is 60 degrees. That's basically what the protractor postulate is saying, is that we can find the measure of any angle by taking the sides and putting them in one-to-one correspondence with the protractor and then subtracting the angle measures that they're associated with. So here it is. Let OA and OB be opposite rays in a plane. So notice they're at the bottom, they're at 0 degrees and 180 degrees. OA, OB, and all rays with endpoint O, so I need to add these, can be drawn on one side of AB, that's a line, and they can be paired with real numbers from 0 to 180. So they're saying that I could put rays anywhere. I don't want to put them at the bottom because that's not, my protractor's not down there. So that's what they mean by one side. But I could put them on one side of AB, and then I can pair them up with a real number. And that real number is going to be between 0 and 180 degrees. OA is obviously paired with 0. OB is obviously paired with 180. If it's not one of those, if it's between one of those, then OC is paired with X. OD is paired with Y, and they just named two variables. They could have called them whatever they wanted. And the measure of the angle is the absolute value of X minus Y. Absolute value because we want it to be a positive value. So we could do absolute value of Y minus X, absolute value of X minus Y. We just want to make sure it's positive. We can classify angles, and angles are classified according to their measures. So an acute angle is between 0 and 90. A right angle is 90 degrees. An obtuse angle is 90 to 100. Well, sorry, 90 to 180. And a straight angle is 180 degrees. Now, in geometry, we don't like to classify things. We don't want to talk about things unless they're labeled. For this example, just to get an idea of what acute and obtuse are, I'm okay with the fact that things aren't labeled. If it's obviously acute, I'll call it acute. If it's obviously obtuse, I'll call it obtuse. But I do have an issue with the middle one. So the first one is acute. The last one is obtuse. But I have an issue with this one because in geometry, we should never assume that an angle is right if it's not labeled as right. So if I saw this on a test or a quiz and someone said to classify it, I would say I'd put something that says, you know, I can't classify this. I don't know if it's obtuse, acute, or right. But if I add a little symbol in here, that's my little right angle symbol. As soon as I do that, now I'm telling the person who looks at the picture that that angle is right. Now I can classify it as right. Okay. So we want to make sure when we're looking at pictures we don't make assumptions. You know, the first and the last one are obviously acute and obtuse. I'm okay with that. The middle one, though, I definitely can't classify that unless someone tells me something about the picture or labels it in some way. Congruent angles are angles with the same measure. So we had congruent segments, now we have congruent angles. So again, that's that tie between the equal measures world, equality, and the congruence world. So sometimes we have to go to the equality world to do some math. You know, we might have to add, subtract, multiply, divide, substitute, things like that. And then we'll go across to equality, do all our little mathematical work, and then we'll come back to congruence so that we can then talk about geometric shapes again. And this gives us our tie between the two worlds. The next thing I have is the angle addition postulate. I write it exactly the way it's in the book so that you see it, but I am going to ask you not to actually use part of this because if you do, you end up making a lot of mistakes. So I would prefer, and if you just want to write this one in your notes only, I would suggest that you do that. I would only write this one. If point B is in the interior of angle AOC, then the measure of angle AOB plus the measure of angle BOC is equal to the measure of angle AOC. So basically what they're saying is if I have two adjacent angles, two angles that are next to each other, they share a common vertex, I can add the two smaller angles and get the bigger angle. Okay. I like to call this angle addition postulate, and this is the only way I use angle addition postulate. Our old book, this was the only way they used angle addition postulate. Notice you're not actually adding angles though. Okay, we call it angle addition postulate, we're not adding angles, we're adding measures. Notice they have little m's in front of the angles. This tells me that I'm adding measures. I'm adding numbers. I'm taking like 30 plus 60 equals 90. Okay. The second one, they have a little side note in your book that says we can add two angles and get 180 degrees. The reason why I hate this is the fact that you're adding two angles to get a number. And then what happens is students start adding two angles to get any number. I can add two numbers. If they labeled as 60, I can add the two angles and get 60 degrees. Or I can add the measures of the two angles and get 120 degrees if it's labeled. You cannot. Okay? If you ever on a test or a quiz do this, I give you credit for it because it's in the book. We're following the book. But if you put any number other than 180 in that and call it angle addition postulate, you're going to lose points because that's not angle addition postulate. Really, angle addition postulate is adding two measures to get a measure of a bigger angle. It's not adding two measures of angles and getting a number. Okay? So again, I'm even going to cross it out. I encourage you not even to write it in your notes. We hate that it's in our book. Okay? But if I don't show it to you, people come back and say, but it's in our book, and you're right. You're allowed to use it. It's in your book. But be very, very careful if you use angle addition postulate as it's written on the right. Okay? So here's an example of using angle addition postulate. What's the measure of TSW? So that's actually the bigger top one. If RST is 50 and RSW, oh, they actually give me the big outside one, is 125. So what I'm going to do is I'm going to write what I know. So this is angle addition postulate, if I take the measure of angle RST plus the measure of angle TSW, that should be equal to the measure of angle RSW. And if anyone ever asked me the reason, suppose you're doing a proof, that would be angle addition postulate. Now what I can do is I can substitute. Well, I know that RST is 50, and I know that RSW is 125. And then what I can do is subtract. So the measure of angle TSW equals 75. Do a quick little check. If I take 50 plus 75, do I get 125? Yep, good. Special pairs of angles. We use vertical angles a lot. Vertical angles are two angles whose sides are opposite rays. That's the definition. We are also going to have a vertical angle postulate, which is going to tell us something special about vertical angles, but we're not there yet. But vertical angles just say there are two angles formed by opposite rays. So, for example, 1 and 2 are vertical angles, and angle 3 and angle 4 are vertical angles. Adjacent angles are two coplanar angles with a common side, a common vertex, and no common interior points. So they have to have a common side, otherwise they're not next to each other. They have to have a common vertex so you don't get something like this happening. You don't get like one angle here and then the other angle comes down and goes like that or something like that. So they have to share a common vertex. And they can't overlap. So you can't have one angle be partially in another angle. So they can't share any common interior points. If all of that's true, they're called adjacent. Complementary angles are angles whose sum is 90. The measure of their angles is 90. And supplementary angles are two angles whose measures are 180. Nice, cool way to remember this. I kind of like this. Someone shared it with me a few years ago. Is if you take a look at C, C is half of an S. So if you take two C's and put them together, you get an S. So complementary is half of supplementary. Nice way to remember it. They do not need to be next to each other. So if I was talking about these angles, I would say they're adjacent and complementary. These angles right here are just complementary. And the same over here. If I was looking at these angles, I would say they're adjacent and supplementary, but these angles are just supplementary. So we'll do this in class, just identifying some complementary, supplementary, and vertical angles. The last part, this has assumptions you can make from a diagram and assumptions you cannot make from a diagram. You are allowed to assume from a diagram that you have adjacent angles. So, for example, if I draw two angles, you do not need to assume that maybe there's two vertices down here and I didn't line them up perfectly. And so they really don't share a common vertex. Or maybe they overlap in a little teeny bit, but because it's a straight line and it's really small, you don't notice that they overlap. If I draw two angles that look like they're adjacent, they're adjacent. You are also allowed to assume adjacent supplementary angles. What this allows you to assume is straight lines. So if I draw a line, you do not need to assume, and even if I put an angle on it, you do not need to assume that maybe that bottom line is not straight. Maybe it's not 180 degrees. Maybe it's 179 degrees, but you just can't tell. If I draw a line that looks straight, you're allowed to assume it's straight. So basically that second one allows you to assume straight lines, which is very nice. And the third one is vertical angles. If I draw two angles that look vertical, so I draw two lines crossing, you are allowed to assume that they're vertical angles. This is also kind of like a straight line idea. What I'm saying is if I draw something like this, and then I draw the second one that like that, you're allowed to assume that's a straight line unless it's obviously not a straight line. Like, you don't need to say, oh, well, maybe one of those lines is not exactly 180 degrees, so that they're not vertical angles. Okay, so kind of these last two are what allow you to assume straight lines. Now, assumptions you cannot make. You cannot assume angles or segments are congruent. If I draw two segments that look like they're congruent, you cannot assume they're congruent unless I put a label on there. So now they're congruent. Okay, without that label, we cannot assume they're congruent. You cannot assume an angle's right. So I'm allowed to assume an angle's 180 degrees, but I'm not allowed to assume an angle's right. So if I draw a right angle, it looks like it's a right angle. Unless I label it, you're not allowed to assume it is. And the last one is the one I have the most fun with. And some of the worksheets you'll notice this too. Is you are not allowed to assume that lines are parallel or perpendicular. So one of the things that, so if I draw two lines, and if I was better, they would look more parallel, and I do that, you cannot assume that they are parallel. If I want to say they're parallel, I have to denote that they're parallel. So, for example, this is kind of cool. If I draw two lines that don't look parallel, and I go like this, these are parallel line labels. Draw little arrows. You can do multiple arrows. You can do like 2, 3 if you want to show they're parallel. Those lines are parallel. Even if they don't look parallel, because I have denoted them, I have given that they're parallel, now they're parallel lines. Okay? So if it looks like it's parallel, but I don't put a symbol on it to denote they're parallel, can't assume they're parallel. Even if they look like they can't be parallel, but I put a little note on them, put a little symbol on them that shows that they're parallel, they are parallel, even if they don't look it. And we'll go over this one too. Take a look at it, see what you can do, but what can you conclude from the information? So I want to know, what kind of things am I allowed to say, what kind of things am I not allowed to say from this diagram? And that's it for today's video. Thank you for watching. Have a great day.